Hello, David Hospinall. Again, today we will do application that literally builds 3D geometric sculptures out of sound. So let me just start with a question. What if you could actually see the shape of sound? And I don't mean just a simple waveform, that squiggly line we're all used to. I mean its texture, its structure, its real three-dimensional form. Okay, let's dive right in. What you're looking at here is the architectural form of box, toccata, and fugue played on a classical organ. Just look at it. See how orderly it is? It's like this low-lying cloud that has a real sense of depth and a rich organized structure. Now for something completely different. This vibrant, almost chaotic sphere. That is the isolated vocal track of Freddie Mercury. It is just an explosion of energy, right? It's dense, it's complex, and it fills the space in a totally different way than that organ piece. And finally, take a look at this. It's a delicate high altitude lattice of points. What you're seeing is the sound of a night and gale singing. It's so light, almost ethereal, and it seems to just float high above the others. So this brings us to the big question. Why do these three sounds look so radically different from each other? Well, that's exactly what we're going to deconstruct. Welcome to the Architect's Tour. We're going to break down how these incredible sculptures of sound are actually built piece by piece. To really get how this works, we need to start by looking at the blueprint. You know, the fundamental rules that map the physical properties of sound directly to visual elements in a 3D space. The most important concept you need to grasp is something called the spectral centroid. Now, that sounds technical, but you can just think of it as the center of mass for all of a sound's frequencies. Or even simpler, it's what our ears hear as the sound's brightness. And this right here makes that idea crystal clear. On the left, you've got box organ notes. They have a low spectral centroid. They're deep and rich, so they form that low-lying structure, kind of like polished mahogany. But on the right, the nightingale's chirps have a really high spectral centroid. They're bright, they're piercing, and that creates this high, delicate lattice, almost like a glinting diamond. So the sound's brightness directly maps to its height on that y-axis. Simple as that. But what about the color? Where does that come from? Well, that's determined by the chromog. This is a cool feature that analyzes the energy across the 12 distinct musical notes. You know, C, C, D, and so on. Each of those notes gets mapped to a specific color on a color wheel. And voila, the sculpture gets painted with the music's own harmony. And this table, this is the complete blueprint. Position Y, that's the brightness we just talked about. Position Z, the depth. That's the spectral bandwidth, basically how spread out the sound's frequencies are. The size of each little point, that's its loudness. It's RMS energy. And the color, of course, represents the musical note. With the x-axis just being time moving forward, every single point is placed exactly where it should be, according to these rules. But visualizing the sound is really only half the story here. This application also has an AI that is actively listening to and classifying what it's hearing. And its vocabulary is, well, it's immense. The AI model it uses, Google's YAMNet, is trained to recognize a staggering 521 distinct audio categories. I mean, we're talking about everything from a sneeze to a sitar, from a choir to a chainsaw. Now, trying to display 521 different classes would be a little much for this kind of visualization. So the project's architect came up with a really clever aggregation strategy. The system takes a specific YAMNet prediction like birdsong, and then it maps it to one of three broad perceptual categories: musical instruments, human voice, or in this case, bioacoustics. Okay, but what if the sound isn't music or a voice or an animal? This is where a really robust fallback mechanism kicks in. Instead of trying to force a sound like a siren or an engine into the wrong bucket, the system just displays the specific accurate label right from YAMNet. No misclassifications, just clarity. Okay, let's put on our software architect hats for a minute. Doing all this complex analysis and 3D rendering in real time, That's a huge challenge. If you get it wrong, the app just grinds to a halt. So, how do they achieve that smooth experience? Well, it all comes down to architecting for flow. The most important thing here is to avoid a blocked user interface. The simple way to build this would be to run everything on a single thread. But the second you start processing audio, the UI freezes up. We've all seen that. The solution is to offload all that heavy lifting to a background worker thread. That keeps the main interface completely fluid and responsive. And this table shows you that exact principle in action. This is the application's non-blocking pipeline. Just notice how all the CPU-intensive jobs, loading the file, extracting all those spectral features, and running the AI inference are all handled by a background queue thread. That leaves the main threads totally free to handle audio playback and render that visualization without a single stutter. Now, this architecture is built on a really powerful stack of open source libraries. PyQt6 provides the core application framework, all that complex audio analysis that's handled by the legendary Librosa library. High-performance 3D rendering is done with PyQgraph, which uses OpenGL, and the AI itself runs on a super efficient TensorFlow Lite runtime. And that pretty much wraps up our tour. But the best part about a project like this is that you don't have to just take my word for it. You can go and explore it for yourself. This incredible tool was created by Oscar David Hospinall R. The entire project is open source. You can find it on GitHub, download the code, run your own audio files through it, and really see how it all works under the hood. And hey, if you want to go even deeper, the project's documentation points you right to the academic papers and technical resources that form its intellectual foundation. Everything from the original audio set paper that made the YAMNet model possible, all the way to foundational research in sound cognition. So, this leaves us with one last big thought. Now that we have the tools to see the hidden architecture of sound, what other invisible worlds do you think we should visualize next?
Long ago, the sky was bruised, the wine was bled, and there you led me on. In your house, I long to be, room by room, patiently. I'll wait for you there, like a stone. I'll wait for you there, alone, alone. And on I read until the day was gone, and I sat in regret of all the things I've done, for all that I've blessed and all that I've wronged. In dreams until my death, I will wander on in your house. I long to be, room by room, patiently. I'll wait for you there, like a stone. I'll wait Hoy la calle la dejamos es barata. Y sería cabrón que tú me toques el guiro. Yo veo tu nombre y me salen suspiros. No sé si son petardos o si son tiros. Mi blanquita, perico, mi kilo. Yo estoy en PR tranquilo. Pero debí tirar más fotos de cuando te tuve. Debí darte más besos y abrazos las veces que pude. Ey, ojalá que los míos nunca se muden. Y si hoy me emborracho, pues que me ayuden. Debí tirar más fotos de cuando te tuve. Debí darte más besos y abrazos las veces que pude. Ojalá que los míos nunca se muden. Y si hoy me emborracho, pues que me ayuden. Ey, voy a estar con abuelo todo el día jugando dominó. Si me pregunto si aún pienso en ti, yo le digo que no. Que mi estadía cerquita de ti ya se terminó. Ya se terminó. Ey, que prendan las máquinas pues pasan dulce. Aquí todavía se da caña, chequeate la baby, diablo, mami, qué dulce. Take a look in the mirror and cry, Lord, what you doing to me? I have spent all my years in believing you, but I just can't get no relief. Lord, somebody, ooh, somebody, can anybody find me somebody to love? Yeah. I work hard every day of my life. I work till I ache my bones. At the end, I take home my heart and pay all on my own. I go down on my knees and I start to pray till the tears run down from my eyes. Lord, somebody, ooh, somebody, can anybody find me somebody to love? Every day I tried, but everybody wants to put me down. They say I'm gone crazy. They say I got a lot of water in my brain. I got no common sense. I got nobody left to believe.